So as I said in the previous video, in discussing electronic spectra of transition metal compounds, we have to kind of roll back and look at free ion term symbols first to sort of get an idea of how these are systematically named and what all of these term symbols actually are referring to in the first place. And what they're referring to are microstates that have the same energy. And that's not going to be obvious what that means. So let's just talk about the multi-electron problem in carbon, which is basically as you know, a 2p2 valence electron configuration. So as you know, we have to sort of work this out in terms of carbon. So fortunately, you can basically ignore the 1s2 and the 2s2 valence electrons in carbon and core, 2s2 valence electrons, the 1s2 core electrons in carbon. The completely filled orbitals do not have any influence on this problem. So what's going to happen ultimately is that the P2 configuration, remember, is typically written this way. And if you remember, the values of M sub L here are typically given as +1, 0, and -1. And that's going to mean something when we start, kind of thinking about how do we put these into different classifications in terms of their microstates. So this is, for example, a triplet state, and we always write that as the ground state because we're minimizing repulsion or electron-electron repulsion, and we're maximizing electron exchange. But let's actually look at all the possible microstates that can be generated from this configuration. And the idea of this being is that what we're looking at here is these are the orbital angular momentum values, of course, as ml. And then the electron being spin up will have an ms value that's equal to +1/2. And then if we have the electron spin down, the ms value will be -1/2. So you're going to see that this all has consequences to the different electron configurations that you can write and their respective energies. So let's figure out how to do this. So there are going to be, just the big answer is going to be, there's going to be 15 distinct microstates for the P2 configuration. We're going to just write them all out on the next slide. But what I want to tell you is there is an equation that can calculate the number of microstates. And really all it's doing is it's describing the occupancy of the electrons in the available orbitals. So really the number of microstates is basically equal to I factorial divided by J factorial times I minus J factorial. So what does this really mean? Well, I is the number of the possible ML and MS combinations. So just thinking about this, we have effectively MS can be plus or minus 1/2. And then we have 3 possible p orbitals to put them in. So you can put, obviously, the spin up electron in the first orbital, in the second orbital, or in the third orbital, and you can put the spin down electrons in the first orbital, second orbital, or third p orbital. And as you can see, that's this number of 6, which comes about here. And then just plugging everything else in, we also know that we have a number of electrons here is 2. So if you put everything in, do the calculation, you'll see that lo and behold, there's 15 microstates. And we're going to write them out anyway. But what I want to also tell you is that what we're going to look for now is there's going to be new quantum numbers for the multi-electron configurations, which are now capital M sub L and capital M sub S. And those are just going to be the sums of effectively the ML values and the corresponding MS values for putting the electrons in these different configurations. And this will make more sense once you actually write them out, which is what we're going to do on the next slide here. And as you can see, I have an empty slide because I just want to illustrate to you how straightforward this process is. So if you think about it, we have p orbitals, and I'm going to do these in sets of 3. And remember, I'm not going to rewrite this a million times here, but remember, we'll just say that the first orbital is going to have an ML value of +1. The second orbital will have an ML value of 0, and the third will have an ML value of -1. And that will serve as like the key to the whole thing. So now let me, sort of write out, all of these possible configurations. So what I'm going to do is I'm going to just clear that so that I have plenty of room to write. And when I do this, I want you to kind of just see that when I actually, write these out, I'm not doing anything other than just distributing the electrons in all the possible configurations while obeying, sort of the Pauli principle and Hund's rules. So ultimately, what can I do? Well, I can basically put the electron pair in the first orbital, in the second orbital, or in the third orbital. So that's 3 microstates right there. And of course, these are going to be singlets. So let me continue to write some more singlet configurations for those p electrons. So for example, I can put the first one as an example, spin up in the first orbital, spin down in the second one. Then I can just keep it spin up in the first orbital, put it spin down in the third orbital. Then I'll just put it spin up in the second orbital and spin down in the third orbital. And those again are all singlet-based configurations. So what else can I do? Well, I can reverse the trend. So instead of putting a spin up electron in the first orbital, I'll put a spin down electron in the first orbital and just reverse everything. So as you can see, these are just the complementary pieces of what I just drew. Again, that's another set of 3 different microstates. They're all singlets. Okay, and then if you kind of start looking at this, I cannot write any other singlet configurations because I'll just be writing over the same configurations again, and you can't do that. So what's left? Well, now I can have everything spin up, and I can kind of do the same treatment again of keeping these spin up in those orbitals, spin up in those orbitals, and then spin up in those orbitals. And of course, those are all triplet states. And then magically, I can do the remaining 3 configurations, because if you notice now, that was 12. These last 3 will be 15. Now I'm just going to reverse this. I'm going to do everything spin down. And you can kind of see how easy this is to write out by hand when you're, when you're just kind of thinking about how do I put these 2 electrons in these configurations, and then no 2 electrons can have the same quantum numbers. So this is what I have. Now think about what this actually means. Is in the cases where I have singlets, I don't even have to worry about this calculation. What do I have? If they're singlets, it's basically telling you in every single case, it doesn't matter where the electrons are, the value of ms is 0 in all of those cases. And that's really straightforward, right? That's very easy to figure out. And then what are my values of ml going to be? Well, obviously, if this one here is on the first one here, thinking about where that electron are residing, they're both in the +1 ml orbital. So this is an example of where the ml value is actually going to be 2. In this one, the second configuration, the ml value has to be 0 because they're residing in the ml 0 position. And then if this is -1, this is where ml will be -2. And you kind of get that that's where these numbers are coming from. So I'm just going to write underneath each configuration what the ml values are, and I'll just kind of collect the ms values off to the right when I'm done. So let's just continue this process. So if you start to look at this, in this particular case, it's +1 +0. So the ml value there is 1. This one is 1 and -1, so that value is 0. And then this one is actually 0 and -1, so that's got an ml value of -1. And this sort of gets boring, but you can see that the configurations are, and why I lined them up this way is it's easy to sort of keep track of where everything is. It's just the same ML values as I kind of walk through there. And then we can kind of continue into the triplet configurations too. You see the electrons are occupying the first two orbitals. So in both of those cases, the ML values are 1. In these cases here, they're still 0 because it's 1, you know, and then -1 gives you 0. And then these are, again, all -1s. So it's really easy to sort of keep those values straight. And then all we have to worry about now is what about the MS values? Well, obviously, these are both in this first triplet here. These are all +1/2. So the MS values in all of those cases are all 1. And then when they're spin down, they're -1/2. All those values are -1. So now you kind of see where we're going here is the basically largest values and smallest values of M sub L really run the gamut from 2, 1, 0, -1, -2. And then the MS values here run the gamut effectively from 1, 0, -1. And then that's going to allow us now to sort of group everything together into their individual microstates. But that is how you determine the ML and MS values for any given electron configuration in the P2 format. And as you can tell, there are 15 individual microstates. And I'll tell you, these get grouped together into 3 energetically equivalent portions. So how do you do that? So let's look and go back to the textbook example. Don't worry about the term symbols for these yet. But basically what I want you to see is if I now just put the ML values on the left axis, so you can see there's +2, +1, 0, -1, -2, and then I put the MS values across the columns on the top, and those are all the possible values. What you're now looking at is everything we just did on the previous slide is just laid out here in tabular form. And the idea really is that when you have this set up in this way, you can actually decompose the term symbols from this information. And the key thing to recognize here is where I wrote out the configurations, here they're using shorthand. So what this means here, for example, is that is if the electron, the first electron is in the first orbital and it's spin up, that's why it's 1+. And then see where it's 1-, that's basically telling you that's in the same orbital, but what else is happening? It's actually got to spin down, -1. So what do you get from that? Plus and minus gives you effectively a singlet state. That's why MS is 0. And then what happens? Well, they're both electrons in the first p orbital, so that gives you the ML value of +2. So you can kind of see that's exactly what we just did. And it's illustrated here. It's just they're using a shorthand on this particular table, whereas we wrote out every single configuration. And you'll notice that there's some symmetry to this. And the symmetry of this is going to be pretty interesting because what you're going to get from this is you can only start picking out things if you sort of recognize that, well, when it goes from +2 to -2, that looks familiar, right? Those are the same. If you had five orbitals or 5 atomic orbitals, what would those 5 atomic orbitals be? They would be the d orbitals. Guess what? That's a d term. So you see it's got corresponding values to what we normally would name the orbitals after, again, the values of L. And that's really what this comes down to. And then if you kind of decompose this again, you'll see that, oh, well, you can have values between +1, 0, and -1. That's the same as what you see in p orbitals. That's a p term. So the d term was shown in that particular case, and then you have a p term. And then guess what? If you have values that sort of run between just 0, what happens when L is 0? It's an s orbital, and that's an s term. But we'll get to that later. But then there's another thing that comes up here. If you look at this, the D term only has entries in +2 and -2 in the singlet realm. So you know basically that the D term can only be a singlet. That's why I have it written here. These are all the singlets. So one out of each of these, one of these categories, or one entry out of each of those boxes belongs to the D term, and it has to be a singlet D term. Then you see that the P term will go from +1, 0 to -1, and you see there's a lot more entries, but what you gather from this is that because of that, the P term is actually going to be a triplet because it has associated with it in these columns. You'll see that that's where the MS values go from -1, 0 to +1. So that's telling you that that's a triplet. So that's called a triplet P. And then when you kind of see what's left, there's only going to be one value left, and it's going to be matched up with 0, and that's going to tell you that you have a singlet S term. And then you sort of gather, like, this is exactly the process of how you decompose this into all the individual pieces you need. So the way to think about it is, if you now look, and instead of like writing out the configurations, just use X's, you see how the D term, apologize for that. You see how the D term here is only going to be these entries. And that looks like, if I turned it by 90 degrees, you'd be looking at like a d orbital configuration. But you see what happens, and that only has values of MS being 0. So that's the singlet D term. Then if you kind of go beyond that and then see what happens with the triplet is a triplet P, right? So what that's telling you is there has to be 9 microstates associated with that configuration. And then if you bring it down, that gives you the MS values that can be -1, 0, +1, but it also gives you the ML values that can only be between +1, 0, -1, and that gives you the triplet P term. So that's really straightforward if you think about it. And then there's only one value remaining, and that is simply drop down here. That's it. That's your singlet S. And then you can kind of see what will happen. So these are 15 microstates. The singlet D has 5 microstates. The triplet P has 9 microstates, and the singlet S has 1 microstate. Adding them all together, adding them all up together, you get 15. And that was the whole point of this, is that there's 15 microstates. 5 of them are matched up with 1 energy. 9 of them are actually degenerate in the triple P term, and then there's a singly degenerate one in the singlet S term. So what you get from this is there's 15 microstates broken up into 3 different energies that are then subjected to some other information, which we will talk about in the next video. Thank you.